Every single day, India generates 147,613 metric tons of solid waste. That volume is projected to reach nearly 388 million tons annually by 2030. Yet despite operating modern municipal collection systems, the national processing rate remains stalled between 22 and 28. When municipal systems lack planned segregation at the source, these three streams are forced together in the same collection bins. Chemically, the organic moisture from the biodegradable waste bleeds into and corrupts the dry combustible materials. By failing to separate these materials at the household level, municipalities instantly destroy the economic and thermodynamic viability of all downstream waste-to-energy technologies. The Solid Waste Management Rules of 2016 were drafted specifically to address this mixing problem. The core mandate of these rules is a strict legal requirement for generators to separate their waste into three distinct streams before handing it over for collection. This pyramid illustrates the solid waste management hierarchy, prioritizing reduction and reuse at the apex, leaving unsanitary landfills at the bottom. When the organic fraction is forced to the bottom, anaerobic decomposition generates massive amounts of methane, while heavy metals leach into the soil. The intended sustainable method for this organic waste is biological degradation, processing it through controlled aerobic or anaerobic composting. Meanwhile, the 32% non-biodegradable dry fraction requires an entirely different approach: waste-to-energy processing. Solid waste management is ultimately a thermodynamic sorting problem. Moving waste up the hierarchy requires isolating wet mass from dry mass long before they reach processing facilities. At a national level, the Ministry of New and Renewable Energy estimates that over 500 megawatts of power can be extracted from municipal solid waste. This chart maps out how that energy is recovered, splitting into two distinct waste-to-energy architectures: biochemical and thermochemical. The biochemical branch relies on processes like anaerobic digestion and fermentation to convert organic matter into biogas and bioethanol. However, this pathway faces strict engineering limits. It only works on starchy organics, requires long recovery periods, and demands high capital costs. While biochemical systems effectively recover energy from organics, they cannot process the rapidly growing volume of complex, dry plastics and synthetic materials. To process the dry, non-biodegradable fraction, facilities must utilize the thermochemical branch. The first option here is incineration, the controlled, high-temperature oxidation of waste. Incineration is simple to operate, but it yields poor economic returns and generates significant atmospheric pollution. A more advanced method is pyrolysis, which heats waste without oxygen to extract bio-oil from plastics. The third method, gasification, directly converts the material into synthetic gas, primarily composed of hydrogen and carbon dioxide. Despite their high energy yields, both pyrolysis and gasification suffer from massive capital costs and severe operations and maintenance issues when scaled up to handle municipal volumes. Because the economics of these thermochemical processes are so difficult to master, municipalities often abandon waste-to-energy projects entirely and default back to open landfill dumping. Even a perfectly functioning waste-to-energy plant is not equipped to handle specialized streams like electronic waste. Globally, 50 million tons of e-waste are generated every year, and India currently ranks as the third largest producer. A standard cell phone or computer contains highly valuable materials, averaging 50% plastic and 15% copper, alongside trace amounts of lithium and cobalt. Extracting these materials involves extreme mechanical hazards, particularly when dealing with components like cathode ray tubes. Physically breaking these tubes or removing solder releases neurotoxic lead into the air as a fine powder, affecting renal function and mental development. There is also a severe thermal hazard. Incinerating PVC cable insulation to recover copper wiring releases highly carcinogenic dioxins and furans into the flue gas. Subjecting e-waste to standard physical or thermal municipal processing turns otherwise contained materials into weaponized airborne molecular toxins. To prevent this toxic release, regulators rely on an economic strategy called Extended Producer Responsibility, or EPR. EPR shifts the financial and logistical burden of collecting packaging and e-waste off the municipality, placing it strictly on the brand owners and manufacturers. The 2016 rules push this requirement for source segregation to its absolute extreme in the medical sector. This matrix maps the rigid containment system for biomedical waste. Yellow, red, white, and blue bins guarantee that specific hazards are isolated and routed to exact endpoints, from deep burial and autoclaving to chemical treatment. Whether dealing with infectious biohazards or heavy metals, specialized waste streams require closed-loop life cycles that remain completely isolated from the standard municipal pipeline. When local processing fails and these toxins enter the water or air, the pollution scales rapidly from a domestic issue into a transboundary crisis. To contain this global flow, the international community relies on a triad of interlocking treaties. The Stockholm Convention mandates the strict restriction and elimination of persistent organic pollutants, directly targeting the dioxins released by improper e-waste burning. The Rotterdam Convention enforces the prior informed consent procedure, ensuring shared responsibility in the international trade of hazardous industrial chemicals. And the Basel Convention utilizes a ban amendment to prohibit wealthy OECD nations from exporting their hazardous e-waste into developing countries. When domestic EPR regulations and municipal processing systems break down, this treaty triad acts as the final failsafe, restricting the movement of toxins across borders. This brings us back to the 72% of Indian municipal waste that remains entirely unprocessed. Sustainable waste management relies on a rigid alignment of thermodynamic engineering with legal regulatory enforcement. Solving the processing crisis requires perfect source segregation to protect waste-to-energy economics, strict enforcement of EPR to capture toxins, and unwavering compliance with the global treaty triad to protect human health.